Why is it that being hit by Mr. Laguerre would hurt more than being hit by Brian? And why is it that, despite my best efforts, I can't become an offensive lineman on the Oak Hall football team?
To answer these questions, we must explain the concept of momentum. Momentum is defined as a vector quantity that is a product of an object's mass and velocity.
Now, we will demonstrate momentum through the following experiments. To start, we use an object of relatively low mass launched at a relatively low velocity.
Ow!
You can increase momentum by increasing velocity.
That really hurt.
You can increase momentum also by increasing mass.
That really hurt.
Now, if we increase both mass and velocity...
So, let's slow down and review for a second. Momentum can be thought of as the amount of oomph that an object has. Thank you, James. The equation for momentum, P equals mv, where P represents momentum, m represents mass, and v represents velocity, shows that momentum is directly proportional to both mass and velocity.
In terms of units, momentum can be expressed as kilograms times meters over seconds, which can also be expressed as a Newton times a second.
It is through this unit conversion that we can directly relate change in momentum to the concept of impulse.
In this experiment, we will demonstrate how impulse is expressed through hitting a golf ball. By doing this, we will examine the relationship between impulse, force applied, and time. I will hit a low force, low time shot. James will hit a low force, high time. I'll do a high force, low time.
Explain clarification.
And James will do a high force, high time.
For explanation, time in this experiment is the amount of time the ball is in contact with the club head.
In conclusion, increased impulse is a result of increased force, increased time, or both.
Thus, impulse equals force times time. From the units for impulse, newtons times seconds, we can see that impulse equals the change in momentum. When an object exerts an impulse on another object through a collision, causing a change in momentum, the net momentum before the collision equals the net momentum after the collision. This is the law of the conservation of momentum.
Wow. The law of conservation of momentum and how it relates to collisions. Interesting stuff. If only I had a lab to demonstrate this. We can explore conservation of momentum through the following two types of collisions. During an elastic collision, the objects bounce off of each other after colliding. In an elastic collision, the momentum of object A before collision plus the momentum of object B before collision equals the momentum of object A after collision plus the momentum of object B after collision. Let's see what this looks like when we demonstrate it. Wow, look at that. Under ideal circumstances, both kinetic energy and momentum are conserved during an elastic collision. The second kind of collision, inelastic collision, occurs when the objects stick together after colliding. During an inelastic collision, the momentum of object A before collision plus the momentum of object B before collision equals the combined masses of both objects after collision times the velocity of both masses combined after collision. Let's see what this looks like. Pretty cool, huh? Even under ideal circumstances, kinetic energy is not conserved during an inelastic collision due to the rebound bouncing that occurs between the objects immediately following collision. Momentum, however, is conserved.
Thank you for the explanation, Ben.
Fun explanation.
This is the end of our video.